Guys, last week we talked about the portal method, okay, and we left off at this problem here. So remember the portal method, the one thing you have to remember is this, two things, okay, how to distribute the column shares. And it's very simple. You just have to remember the internal columns take twice the force of the external columns. And the other thing that's very important is that the bending moment diagram goes through the middle of the member. That means you've got zero bending moment at the middle of the columns and the middle of the beams. That's the assumption. And from that, you can pretty much solve everything else. So in this case, we did it last week. The first thing we did was, for this problem here, we found the column shares, right? That's the first thing. And you can see the column share here takes twice the load, takes twice the lateral force of the external columns. Okay, and obviously the column shares build up as you go down the building. Okay, so you get the column shares, which is twice as much in the interior as the exterior column. So I think all of you managed to do that okay last week. And from that, you can easily get the shear force diagram. It's just this force times half the member length, right? So very, very simple. You just have to do it for one side, and the other side has to be the same because the line goes through the 0 point in the middle of the column or the beam. Okay, so there you have it there. So we left off at this point last week. Now we have to get the beam shares. So let's do that. If you haven't done it from last week, copy this down, and I want you guys to put in the beam shares. Okay, so copy this figure down now, and you've got enough information to get the, not the beam shares, I mean the beam bending moments. Okay, so if you guys could do that. So copy this down and then complete the beam bending moments. Okay, let's have a look at this. Now this one here is obviously, you've got, at this joint, you've got an anti-clockwise moment of 8 kilonewton meters. So you've got no choice. You have to have an 8 kilonewton meter clockwise moment on this beam. Okay, so we've got that. So that's 8 there. And this one here, you've got 8 and you've got 25 there. So what do you have to balance it? You've got 8 anti-clockwise plus 25 anti-clockwise. So you need 33. Okay. Clockwise to balance it. So these two beams are done. Now it's easiest to go to this part here, isn't it, to balance it on this side. So this one's also 8 kNm. This is anti-clockwise. This is clockwise on the beam. So that top beam is done. And this one here, it's just 25 plus 8, 33 again. So it's easier to go to this end one rather than figure it out in the middle. Okay, so let's see what we have here. We got 8, 8, 6, 8, 8 on that beam, 33, and obviously that's 33 there, 33 here, and 33 here. So that's your beam moments. Now to find your shear forces, okay, you can do it, the shear force is very easy. You just get the reaction at each end. Now what's the reaction at each end? You just get the moment, the total moment, this plus this, 2 times the moment at one end, divided by the length. Very easy, right? So this would be what you got, 25 times, what's the length? 25 times 4, 100. Okay, 100 divided by 4. So you've got, hang on, let's have a look here. You've got 25 plus 25 is 100 divided by 4. Of course, it's, so you got a reaction here. Just hang on, just have a look at it again. You got 25 on the end here. Okay, plus 25 is 50. Oh, sorry, 50 divided by 4, brain stop. Okay, so they've got a total moment of 50. Okay, 25 plus 25 and divided by the length is 12.5. It's very, very simple to find the shear force. Okay, so you just get twice the moment divided by the length. Now look at this one, twice the moment, 50 plus 50, or 2 times 50 divided by the length is 25, obviously. So you got shear force of 25. And this end one here, well, we've already done it for 25, so it's the same. Now let's look at this one here. You've got 8 and 8. Okay. So just what was the height of that? 3.2. So you've got 8 plus 8, 16 divided by 3.2. Okay, so that becomes 5. Okay, so we've got 5 share here, 5 share. And this one here, you've got 16 plus 16 is 32 divided by 3.2 is 10. Now for the beams, you do exactly the same thing. You got 33 kilonewton meters on the end, so multiplied by, you can multiply it by 2, we just divide it by, what have they got here, 16.5. So the way they've done it is, okay, over here, what we've done here is 33 divided by half the length, which is the same as twice the moment divided by the whole length, okay? So the other way do it is 33, 60, that's the same as 66 divided by 4, obviously, okay? So, and you do the same for the other beam. So very simple, just add the moments up, divide by the length, or just use one of the moments and divide by half the length. It's up to you, okay? Any questions on that? Okay, so I want you to, I think this is the last example. Okay, example 6. Okay, let's do, how many more examples? Let's do example 7, okay? I want you guys to do this entire example. This is like what you get in an exam, okay? So first thing is to get the column shares, then get the bending moments, get the column shares, draw the free body diagram if you need to. Some of you won't need to, you'll be able to do it by inspection, and then do the shear forces, okay? So I'll pretend this is in an exam and I'll give you 15 minutes to do this. I'll make it 20 minutes to do this problem, okay? So give this one a go. It'll definitely come up in an exam. Okay, so you divide this up into 4 columns. So you've got 1, 2, and the ones here, you've got 2. The middle one takes twice as much as the side one. So for the top part, you've got 40. So if you divide it by 4, it's 10. So 10 goes to the externals and 20 to the internal. And then you've got 120, right? So 120 divided by 4 is 30. So you've got 30 on the externals and 60 in the middle column, okay? So that's what we've got there. And it's very simple now to do the bending moments. It's just one of these forces times half the length, okay? One of these, so this one here was just 10, okay? Let's remember 2.8 and 3.6, so it's 28, 28, 28, 28, 56, 56, and you do the same for these ones. So let's have a look. So you got what's 14. Okay, let's have a look at this again. 10 times 1.4. Okay, so it's 14. Okay, and you got 28 in the middle, and then 14 in the middle. For this one here, again, you just get one of these forces and multiply it by half the length. And that's what you do here, 54, 54, and you've got twice as much in the middle. Very, very simple, the columns, right? Now you just do the beams. Okay, so the beam here is you got 14 clockwise, so you have to have 14 anti-clockwise. Top one's done. Now let's have a look at this this one here. You've got on this side you've got 14 anti-clockwise, so you're going to have 14 clockwise. So you do, once you've got that 14 there, it's going to be, you know, that line goes through the middle, so the top beams are done. Now this one, you've got 54 plus 14, which is 68, right? At this joint going anti-clockwise, so the beam will have to provide 68 clockwise. Then I just move to this side here because it's simpler. You got 14 plus 54 again, 54 anti-clockwise plus 14 anti-clockwise, that's 68 anti-clockwise, and you need 68 clockwise. So 68 clockwise, okay, to and then that just goes to the once you've got that number there, obviously everything else is easy. So you do that really quickly, okay, get all the beam bending moments. Now, what's the rule for getting the shear? Very simple. 54, say this one, 54 times 2, okay, this number times 2 divided by the length, okay, so remember the length there is 3.6, so it's 108 divided by 3.6, you get 30, right? Let's check that. Okay, And so you've got 30 on that side as well, because you've got the same bending moment. You got 60 in the middle, all good. And this top one, you got 2.8, right? You got 14 times 28 divided by 2.8 is 10. You got 10 on that side, and you got twice the one in the middle. Now, what about the beam? Now, let's just look at this top one. 14 plus 14 is 28, divided by 4 is 7. Okay, this is 28 divided by 3 is 9.3. Okay, this one is 68 times 2 divided by 4. Okay, 68 plus 68 divided by 4, 34. This one is 68 plus 68 divided by 3, 45.3 kilonewtons. Very, very simple. You should be able to get a little bit of practice. These should be, when you're in an exam, should be gift marks for you, okay? So that's it for approximate methods. Any questions before we start the next topic? Okay, good. So what we're going to look at now is wind loading. Wind loading's got two parts. First thing we've got to do is we've got to find the wind speed. And the second thing we've got to do is actually from that wind speed work out a wind pressure and convert that wind pressure to a force. So we're going to go through two PowerPoints. The first one is finding a wind speed. So the main steps are determine the design wind speed for the site. And this is based on the return period of wind. And this depends on what we call the importance level and the limit state adopted, the region and the location, the terrain, the alignment of the building, the height of the building, shielding effects, topography. Okay, so these are basically 7 things we look at. Okay, and this is what we're going to go through in this PowerPoint. Okay, let's look at wind speed. Okay, the return period of the structure. The return period of an event is how often on average it occurs. So if you've got a return period of 50 years, you can expect an event's got a return period of 50 years. It simply means that if it can be expected to occur once every 50 years, or twice every 100 years, or 10 times every 500 years, etc., right? Or you could think of it, if it's got a return period of 50 years, each year has got a 1 in 50 chance of occurring, or a 0.02% 0.02 or 2% chance of happening, right? For every year, okay? So the bigger the return period, the more extreme the event, okay? Return period's also got another word name called the recurrence interval. The return period takes into account 2 things: the importance level of the structure and the design working life. So let's have a look at the importance levels of the structure. Oops. Okay, just bring it up. There it is. Okay, so importance level. This is in the code, okay? 1170.0, okay? It's code here, okay? And you can download that. And it tells you it's based on the sort of the usage of what the building of the structure. So if you've got a structure presenting a low degree of hazard to life and other property, it's got an importance level of 1. Normal structures and structures not another importance levels 2. Structures that as a whole may contain people and crowds or contents of high value to the community or pose risks to people and crowds 3. And they give you some examples here, right? And you've got structures of special post-disaster functions. There's obviously medical, emergency, hospitals. Okay, they're much higher, 4. And 5, you might be talking about dams or something that if it collapsed, it caused, you know, a lot of people to die, perhaps. Okay, it'd be a catastrophe. Okay, so such dams, maybe major bridges, that sort of thing. So we've got 5 importance levels, and this we use this to determine, as part of the method, to determine what return period we want. So once we've got this importance level, we go to table 3.3. Let's bring it up. Okay, so you've got the annual probability of exceedance, right? This is where you look it up. You look up the importance level, and you're given the design working life. So if you got a design work, this is what you ask for. If you got a design working life of 50 years, say, an importance level of 3, then your probability of exceedance for wind is 1 in 1,000. Snow is 1 in 250, earthquake 1 in 1,000, and your serviceability is 1 in 25. Now, you can see that as the return period gets higher, typically these values increase as well, your return period. So in this case here, this is a probability. The return period is the denominator, the number on the bottom of the fraction, okay? So 1 in 1,000 annual probability is the same as what? 1,000-year return period, okay? So you got something that happens once in 1,000 years. That means you've got a 1 in 1,000 chance of it happening this year, okay? 500-year, something that happens 1 in 500 years, you've got a 1 in 500 chance of it happening this year, okay? Or you've got a 2 in 500 chance of it happening over 2 years. Very simple concept. So this is where we look up our return period, okay, from this table here. So we get an importance level. You're told what design working life you want, and then you go away and read off the return period. And today we're going to be in particular looking at wind, okay, both for the serviceability limit state and what this is called the ultimate limit state, okay. So serviceability limit state is for what we call deformation of the building, okay. We don't want it to over deflect too much. The ultimate limit state is for the strength design of the building, okay. So we don't want to go, the forces here will typically be greater than the forces for serviceability, because when you're designing for ultimate limit state, if you go beyond that, the building is supposedly will collapse. So in this case here, ultimate limit state, you're designing the building or the members to avoid shear, collapsing under bending or shear. In this one here, you're designing serviceability, you're designing the building so that it doesn't deform too much. It doesn't mean it'll fall over, but you don't want something to, tilt over at an angle too much, or if you've got a beam, you don't want it sagging too much. Okay, so how do we, okay, so we've got this return period and we've got 2 tables we're going to use to do that. So let's look at the equation now, the main wind speed equation. Okay, so this is from, now the wind code is 1170.2. We're talking about section 2.2. Okay, so okay, now what is this? This is what we call the regional wind speed. This is the wind speed associated with the area you're in. So Wellington's obviously, for those of you know, Wellington's going to be a lot more windy than Auckland, or so it depends on where you are, this value here, and it depends on this value R, which is what we just talked about, which is the return period, right? So you look up a table to do that. Then we got this thing called the wind directional multiplier. What this does is take into account for that particular site, the direction the wind is blowing, because depending on at each location, the wind strength will be different depending on the direction that the wind blows, okay, or depending on the direction of your building, the alignment of your building. Okay, so that we've got a multiplier there that takes into account how your building is oriented, okay. The other thing we look at is the terrain height multiplier, okay, how high you are from the ground, basically, and the terrain category. We'll look at this soon. We've got a shielding multiplier. If you've got trees in front of your building or other buildings, that might shield yourself, that might shield your building from the wind, and so you can reduce the wind speed. And you got a topographic multiplier. Are you on a plateau? Are you on a side of a hill, or are you near sea level, etc. Okay, so let's have a look at these 1, 2, 3, 4, 5 factors now, and starting with the regional wind speed. Okay, so you can see regional wind speed here. This is the table taken from 1170.2 in a chart. And you see you've got these different wind regions, okay? Okay, they're quite broadly defined regions, A6, A7, W, and you've got these other ones as well, which are a bit more complex that we're not going to look into, okay? But we basically look into whether you're in region A6, A7, or W. And then, so what you do is once you've got that, you look at down here, velocity, you find the regional wind speed, and you find it according to the return period, okay? So if it was 500-year return period for, say Auckland, where we're in region A6, okay, well, this is A1 to 7, we can use 45 meters per second, okay? And so again, this depends on your location and your return period. Okay, let's have a look at the wind directional multiplier. Okay, this is just for the actual direction of wind within a region. The reference from ASNZS 1170.2. Okay, this is where this is the table from this code, the wind code. Okay, and what we have is these directions, right? And depending on the direction the wind blows, we multiply the wind by a factor. So if you're in region, and now this differs for every region, right? A1, A2, all the way to A7, right? So if we're in region A1, say, whatever value we get from here, we can reduce it by 10% if the wind's blowing from the north, if it's a northerly wind. If it's a southerly wind, we can reduce it by 15%. Okay, so the wind but just to clarify, wind direction is reported in terms of the direction from which it arises. Okay, so this is a northerly wind. A northerly wind comes from the north and blows towards the south. A westerly wind, okay, comes from the west, arises from the west and blows towards the east. And this is the southwesterly, okay? It arises from the southwest and blows towards the northeast. And northeasterly arises from the northeast and blows towards the southwest.
What's the any direction?
Sorry,
what's the any direction there? Like the
oh, okay.
That's
if you want to be conservative, right? That's if you want to be conservative. That means if you don't say, oh, I don't want to take this into account, well, then you have to use 1. Okay.
Okay. Yep.
Okay. This allows you to reduce your wind speed and save perhaps on material or something, right? But if you want to be conservative, you just use 1.
Okay. Thank you.
Okay. We need to adopt the maximum MD within a 45-degree. Okay, so how do you determine? You've got these values here. So what you do is you plot them from 0 to 360 degrees bearing, right? You all guys know what bearing is. So we plot these. So you've got a plot number for 0, you've got number 45, 90, 135 degrees, 180, 225 degrees, 270, 315, and 360. So we've got values for every 45 degrees. So you plot them and you join them up. Now, you've got to say we've got this bearing here, right? A building like this, this has got a bearing this wind has got a bearing of 70 degrees, right? But no wind is exact. So what do? How do we determine the value that we use? Well, it doesn't matter where you are. What you do is, if this is the orientation of your wind direction, your actual wind direction is 70 degrees, we use the largest value within a 45-degree frame, okay? So if the bearing is 70 degrees, we start at 25 degrees and go to 70 plus 45, which is 115. So within this frame, okay, we look for the largest value. So for here, we would use a value of 1 because that's the largest value within this box. We wouldn't necessarily interpolate it. Okay, so you can see here, if you've got a wind direction of bearing 70 degrees, you're going to go between, you need the largest value between negative 45 degrees, 45 degrees on each side of it, okay? You need to look at 45 degrees this side and 45 degrees that side, and it's the largest MD value within this range. Okay, so we've got, we're going to do an exercise soon. We've got velocity based on region, just to recap, and return period. We've got the MD value, and we're going to use the largest one within 45 degrees of the actual wind direction. Now let's have a look at the terrain category, terrain height multiplier. This takes into account the roughness of the terrain that the site is situated on. So obviously, you can imagine if something's more flat, you're going to have higher wind speeds than if something's rough. Okay, now let's have a look at how these terrain categories are described. Okay, you can see you've got 6 different types of terrain category, and the lowest value one, category 1, is you got basically very, very flat terrain or water surfaces, okay? No trees, poorly grassed plains, rivers, canals, lakes. So you know what we're talking about, right? Very open. And so they've got the descriptions here, and by the time you get to this one here, category 4, you've got numerous, so this would like be in the middle of a city, okay? Terrain with numerous large, high, and closely spaced construction, such as large city centres and well-developed industrial complexes. Terrain category 3, you've got terrain with numerous closely spaced obstructions having heights generally from 3 meters to 10 meters. The minimum density of obstructions will be at least, so it gives you some rules there, okay? Another way a better way to look at it perhaps is to look at some pictures. So you've got, let's have a look at this one. Just gives you an idea, it doesn't do it for all of them. Okay, so category 1, category 2. So you get an idea, right? Category 2.5. So I suppose most rural areas in New Zealand would be 2.5. Category 3, okay, built up suburban areas, and category 4 in the middle of a city. Okay, so obviously as you go from 1 to 4, your wind speed will get, you can reduce your wind speed more and more, can't you? Okay. Now this terrain category, in the table, you got in the code, you got terrain category 1 to 4. You've got this row, and then the wind speed will also increase with height. Okay, so the height of your building, so the naturally height will also influence wind speed. Both height and terrain category are combined into one single multiplier, and it's called the terrain height multiplier. So for a given terrain category, you decide on that first. You look for your height of your building, and that's the number that you use to increase or decrease your value. So you can see terrain category 4, you can decrease your value for relatively low heights, right? Okay, whereas for terrain category 1, you've got to increase it for most of the time. Okay, so the wind speed decreases with increasing terrain category, but increases with increasing height. And if you get, say, terrain category 2.5, you just interpolate between two values, right? You get the average value between this one and this one, the terrain category 2 value and the terrain category 3 value. Is there any questions on that? Okay. So let's talk about the wind shielding multiplier. This multiplier takes into account other structures upwind of the building that provide a shielding or blocking effect and thus reduce the wind speed. Thus, the shielding multiplier reduces the design wind speed. It takes into account the spacing of shielding buildings, heights of shielding buildings, and widths of shielding buildings. Okay, so it obviously takes into account basically say the geometry of the buildings that shield you. Outside suburban areas, we typically use MS equals 1.0. Okay, because obviously few buildings, we might as well just use one. Non-permanent items such as trees, etc., cannot be considered to provide shielding because they can be removed and then you don't have that shielding. So buildings providing shielding are close in height to the height of the structure being shielded. These shielding buildings must be within 20 times the height of the structure. So these are some rules. We're not going to go into it in detail, but I just want you to know what shielding multiplier is. Okay. For our purposes of this course, because we're just skimming the surface of it, we will be conservative and adopt MS equals 1. So if we adopt 1, we're being conservative because we're not reducing the wind speed, right? We're using the, the shielding multiplier obviously reduces the wind speed, but conservative means we'll take a more careful approach, okay? And we'll just use MS equals 1. Topographic multiplier, okay? If a structure is built up on a hill or other raised topographical feature relative to its surroundings, such as an escarpment, then the wind speed may be required to be increased, okay? So you could get a structure like this, okay, built up on the side of a hill. Okay, what's an escarpment? Okay, something like that. Okay, obviously you can imagine, okay, the wind's going to be quite significant. Okay, okay, so MT mainly takes into account the height and shape of hill or escarpment and the elevation E above sea level. Okay, so there's various rules to determine MT. Okay, so these are found in the code. We're not going to look at it in any detail. If you go continuous structural design, you'll have to know these, but not for this course. Okay, for the purposes of this course, we will assume MT equals 1. However, note that this is not a conservative assumption. If we do build on a hill or area of raised elevation MT, MT must be taken into account because MT is above 1, isn't it? It increases your wind speed typically, right? Whereas MS, like a shielding factor, is below 1. So we'll just assume we're not in a hill or area of raised elevation, okay? Okay, so here's an example. Determine the ultimate limit state design wind speed for the site circled below from Google Maps. The location is Onehunga, Auckland. The site is intended for a 2-story block of apartments with a height of 10 meters with a design working life of 50 years. Okay, the wind is a southwesterly. Okay, so just give me a moment. I'm going to get you send you the links to download the relevant information that you need for you to do this assignment yourselves. Okay, so just give me a moment. Hey guys, what I want you to do is copy down this key information, right? The location, Onehunga, Auckland. The site is intended 2-story block of apartments, height of 10 meters, a design working life for 50 years. The windows are southwesterly. So if you can copy this down, just copy that paragraph down, or use your phone to just to take a shot to photo it. Okay, so I'll give you some time to do that. Okay, so I assume you've got the information down. Now, I want you guys to do this. Find the importance level based on the purpose and function of the structure. So I've given you those 2 links. And once you determine the importance level, I want you to find the return period. Okay, so you guys do that and based on the links that I've sent you. Okay, so from its uses, I think you'll find the importance level is 2. So let's have a look at so I've got an apartment building, right? Okay, so let's have a look at, okay, it's obviously not importance level 1, importance level 3. Okay, so it's obviously none of these. Okay, it's not, okay. Is it a multi-occupancy, residential, commercial, including shops, industrial, more than 5,000 people? So it's obviously not that. So looks like it's going to be importance level 2. Okay, so buildings not included in importance levels 1, 3, and 4. Okay, so it's a normal structure. Okay, and from that, it's 50-year return period. So we find the return period. Okay, so importance level 2, return period of 50 years. So for wind, it's 1 in 500, and for ultimate limit state, 500 years, and for serviceability limit state, 25 years. Okay, from table 3.3, for 50-year design life, importance level 2, ultimate annual probability of exceedance is 1 in 500. This means in 50 years, there's a 10% chance that wind event we are designing for will be exceeded. Return period R equals 500 years. Okay, so I haven't asked for the serviceability one. We're just doing the ultimate limit state one for now. So did all of you guys get this correct? No problems? Okay, let's go on to the next step. What we want to do is find the velocity of the wind, the wind region, right? Okay, so we know we're in Onehunga, Auckland, and then we need to find the regional wind speed. So what I'll do is I'll text you those links now so that you can do that yourselves. Okay, so find the wind region and the regional wind speed using the links I gave you. Okay, let's find the regional wind speed. Well, it's just Auckland, right? So you can see Auckland here is part of region A6. Okay, you got region A7 here. We're part of A6. And we've got a 500-year return period. Table 3.1. Okay, so 500-year return period, we're talking about 45 meters a second. You guys all get that? for 500-year return period?
Yep, yep.
Cool. Okay.
But sorry, the winds that is it like the maximum or like an average, like on this column?
Oh, and this got them. Well, this is what you start off with, and then you modify it, right, for various other factors. So this must be a normalized value, right?
Okay.
For the various regions, and then you modify it depending on the individual situation at that location.
Okay.
Right.
Yep.
Okay, so now let's look at the directional multiplier. We've told the wind is a southwesterly. Okay, so let's have a look, just go back to here. The wind is a southwesterly, right? So it's coming, what does that mean? It's coming from the south and the west, right? It's blowing up in this direction, eh? So imagine the side of the buildings like this, blowing up in this direction. Okay, so what is this bearing if it blows southwesterly from east, west to east? Can anyone tell me what the bearing of that wind is? Okay, think about that. Well, it's
45.
hang on. It's coming.
Oh.
No, two. It's very difficult. You got to be careful, eh? Because it depends on your the bearing is still 225 degrees, right? It's coming up this way. Yeah, you could do it, say, as 45 degrees, but I think we call it 225 degrees because that's where it comes from. Okay. Although it looks like, you know, the vector, I suppose, looks like it's 45, but I think when we go southwest, the bearing is 225 degrees. Okay, the wind directional multipliers take into account the fact that the strength of wind will vary with direction within a location. We need to find the maximum MD within 45 degrees either side of the main wind direction under consideration. We do this in the next slide. Okay, so we look at, okay, the bearing is 225 degrees. We find the maximum value of MD between 225 minus 45, which is 180, and 225 plus 45. So we look at the wind bearing between these two angles, right? Now we're talking about region A6. So what we've got to do is we've got we plot that out, and we find a window where this the window between here 180 to 270. What is the maximum value of MD? Okay, that's what we do. Okay, so again we look at this. Plot MD between 5 equals 180 and 270. Okay, now if you plotted it all along here, right? What we're looking at is 225 degrees and 45 on each side is 270, 180. Where did we get this plot from? Well, we started here, north, 0.85, northeast, 0.95, etc. right? So we plot these values on a chart. That's the first thing we do. Then we plot our value, okay, of wind, our wind direction, and go 45 degrees on either side of that. And then you find within this window, what is the maximum? And in this case, it's just 1. So we can't reduce it any, you know, we can't reduce it. We're just using 1 in this particular instance. Is there any questions on that? Okay, let's go to, okay, so you find this maximum value within this red box, and I've done a spreadsheet for it. Let's bring that up. Okay, so in this case, we've got MD equals 1.00 at the degree, at beta equals 270. So we're just going to use this 1.00 here for our calculation. So we've got what? We got the wind speed now, and we've got the directional multiplier. Now, the next thing we need to do is look at the terrain height multiplier, MZCat. So we look at the examples terrain. You got descriptions here. And what I'll do is I'll give you the links for you to be able to solve this part of the problem. Okay, so you've got the information there now, so give this problem a go. Hey guys, what terrain category did you come up with? Anyone got an answer?
0.83. Oh no, so the category
Yeah.
Category 3, no, suburban.
Yeah, I got category 3. Okay, so let's just have a look at that. Something like this, this situation here, right? Yep, looks, it's not a big city, but it's sort of like that. Yep, category 3. And we got the average height of Z equals 10 meters. So let's have a look at that. Okay, so we're here, category 3, 10 meters. So we should get 0.83, right? Okay. 0.83, good. Okay, so we're collecting our factors, aren't we? So now, now for MS and MT, we said that we're going to use 1 for them. We will conservatively adopt the shielding multiplier of 1 because it can go below 1. We are not building on a hill or an escarpment. The area concerned is near sea level. Therefore, we use MT equals 1.0. This is not conservative, but a realistic assumption in this case. Okay, so we've got VR, you've got MD, you've got MZCat. So what is your V site beta? You just multiply those together, right? So 45 times 1 times 0.83 times 1 times 1, and we get 37.35 meters per second. Okay, so I've taken you through that first example. Let's have a break now and come back in 15 minutes, okay? So see you soon. Hey guys, let's have a look at this problem. In this problem, we need to determine both the ultimate and serviceability limit state design wind speeds for this site here. The location is near Christchurch, New Zealand. The site is intended for a 3-story daycare facility for around 200 people. The average height is 15 meters with a design working life of 50 years. The wind speed for consideration has a bearing of 210 degrees. So it's coming from here sort of, right, towards blowing like that. Okay, so the first thing to do is we need to consider the general, the site wind speed. Okay, you need to, but before you do that, you need the importance level and the return period in both serviceability and ultimate limit state. Okay, so what I'll do is I'm going to send you a link now to a document with all the links that you need to solve this problem. So I'll do that right now. So you just download this as soon as I send it. Okay, so just open that document or download it, the document that I've just sent you. Okay, and that document has links that you can click on. Okay, you probably want to download it to your computer. for the importance level, return periods, etc. Okay, so first thing I want you guys to do is determine the importance level and the return period. So if you guys can do that. Okay, let's have a look at the importance level. Okay, so we have a 3-story daycare facility for around 200 people. Okay. So daycare facilities with a capacity greater than 150. So obviously importance level 3. Okay. Importance level 3. Now let's look up the return period for both the ultimate limit state and the serviceability limit state. Okay, so for 50 years, importance level 3. For wind, we've got 1 in 1,000. And for the serviceability limit state, 25 years. So once every 1,000-year wind and once every 25 for ultimate limit state. That's for collapse. And for deflection, every 25 years. Okay. So from table 3.3 for a 50-year design life and importance level of 3, the ultimate limit state and the annual probability of exceedance is 1 in 1,000. Okay. This means in 50 years, there's a 5% chance that a wind event for the ultimate limit state will occur. The ultimate limit state return period RULS therefore equals 1,000 years. Now for the serviceability limit state is 1 in 25. This means in 50 years, the wind event for the serviceability limit state will happen about twice. Okay. SLS return period RSLS equals 25 years. This is not exact actually, how we just split it up, because for a 1,000-year wind, you could have 1,000 years you don't have anything happen. Okay, it doesn't get to a probability of 1 because you have 1,000 years. If you have 2,000 years, right, you might have a 1,000-year wind happen in the from 0 to 2,000 years. You might have 2 winds, which give you a 1,000-year return period, but those 2 winds might occur in the last 500 years. Who knows, right? So it doesn't always mean it happens like clockwork. There's nothing definite about this. It just means that from the records, on average, a wind occurs every 1,000 years, right? Doesn't mean that, hey, your 1,000 years is up, you've definitely had a 1,000-year wind. It doesn't actually mean that. So these are really sort of approximations, okay? These probabilities. Okay, so it'd be good if you could write those down, okay, if you haven't already, okay. Or you probably can remember 1,000 years, right, for ULS, and SLS 25 years. Now let's go on to the wind velocity, okay. So you've got the lengths I've sent you, determine the wind region and the regional wind speed from table 3.1, okay, so you guys do that. Okay, let's have a look at the wind region. Okay, so we're in Christchurch, so that will be wind region A7. Okay, so the wind region is A7, and let's find the regional wind speed for A7 and 1,000 years. Okay, so we get 46 meters per second. That's for the serviceability limit state. Now for the this is the ultimate limit state. Now for V25, which is the serviceability limit state, we get 37 meters per second. Everyone all good with that?
Yeah, for the final answer, we give like answer in kilometer per hour or meter per second, like for
this meters per second.
Okay.
Yep. Okay. Now the bearing is 210 degrees. Now, interestingly, someone asked me a question before, and I suddenly thought about it. I said, yeah, it was a good question, because if the wind comes from the south, say in this case, it's the south, more or less the southwest, isn't it? Because normally if you have a vector, the bearings from the north to the vector, but we take it from, this is actually, we take it the other direction. And I looked it up while I was in the break because it was a good question. And this is actually the way we do it for wind, right? Okay, so if you've got something like northeast, that would come from, that means it blows from the northeast and goes towards the southwest, and that's 45 degrees. So if you've got something like southwest, I don't know what that means, south by west, or say southwest, yes, it is 225 degrees. So it seems that is the way they do it for wind, okay? But it was a good question, okay? So in this case here, what is the bearing of this? It's 210 degrees. Now, what range of directions do we need to find the maximum MD for? Now, can you remember it's plus or minus 45 degrees, right? So it's these red lines here. Now, if this is 210 degrees, what is this bearing and what is that bearing? Well, I can just tell you it's 210 minus 45 is 165 and 255. And 210 plus 45 equals 255. Now, what I want you guys to do is actually plot between, plot over that region, okay? So if you've got one, you can plot between, for 180 degrees, 225 degrees and 270 degrees, okay? So let's bring up the table there of the MD values. Okay, I won't give the answer, so 3.2. Okay, so you know you're in region A7, right? Okay, so region A7. Okay, so we're going to be interested in between, say, south and south. So I'd plot it for, this is, if south is 180, southwest is 225, and west is 270. So maybe plot, just sketch it for those, get a chart and just sketch it and get the value of MD, okay? See if you can find the value of MD. You might have to interpolate. Okay, I'm not exactly you might have to interpolate, right? Okay, so you need to find the values between the maximum value between 165 and 255. So you got south, southwest, and west. So you just got three values you could plot for A7 to see if you can find the maximum value between 165 and 255. Is that okay, guys? So remember, south is 180, southwest is 225, and west is 270. Okay, is that okay? So plot that 0.9, just get a sketch and plot it and see if you can find, and then get the maximum value between 165 and 255. Okay, so you guys give that a go. Okay, so you know it's between 165 and 255, and you know it's region A7. Okay, let's look at this. What if we plot this? Okay, so it's in this region here, isn't it? Okay, so you've got 1.9, and then it goes up to 1. So from 270, between 270 and 180, right? Oh, actually, we should have got a bit lower, but it doesn't matter because it's 1 all along anyway. So you got 1, and then it goes up to, sorry, 0.9, it goes up to 1 here. So we put this window here between from 210, okay, 45 degrees on either side. So it's from 165 to 255. So the highest value is at 255, isn't it? Now that means you're going to have to interpolate between here and here. So how do you interpolate? From interpolation, okay, this is how you interpolate. You go 0.9 plus the vertical distance between them, and then how much of the horizontal distance has elapsed as a percentage, right? So that's an interpolation formula, and we get 0.97. Okay, so if you don't know how to interpolate, it's very simple. Just Google it. You should have done it in your first year maths or whatever. Okay, it's not a difficult thing to do. It's a little bit of number crunching though. Okay, so we get 0.97 for MD. Now for your MZ cat, here's the picture again. I've given you the picture, so you have to go back. you've got the links. So I want you to get MZCat, okay, adopting a average height of 15 meters. So give that a go. Okay, look at the examples of terrain here. So what do you think we've got? I'd say 2.5. Okay, so yep, terrain category 2.5, and Z equals 15 meters. So from that table, okay, so terrain category 2.5 and at 15 meters. So, okay, well, how do you get 2.5? You've got 2 and 3. Well, you just get the average of 1.05 and 0.89. Okay, so you know, table 4.1, hang on, should show you how to do the calculation. Okay, so 1.05 plus 0.89. 0.97. I should have actually showed you the calculation, okay, but it's 0.97, the average between the halfway between 2 and 3, okay. So we're going to use one for MS and one for MT. Okay, so we just put that all in there. For ULS, we get 43.3 meters per second. And for design, for serviceability limit state, we get 35.1 meters per second. Is there any questions on this? Okay, so these calculations are not difficult. Maybe this PowerPoint, go through it once again, just to get the hang of it, okay, and you should be okay. This will probably come up in a test, okay? So just give me a second. I'm going to bring up the second PowerPoint now. We're going to, what we've done is work out wind speed, design wind speed. The next thing we're going to do is convert those wind speeds to pressures. Okay, so just bear with me for. Okay, so converting wind speeds, we're going to, previous slide again was about wind speeds. We're going to look at how to convert those to wind pressures and then forces in accordance with this code here. Okay, before we start, let's just watch this brief video. Oops. See if it turns on okay. So main steps, we need to first determine the design speed, the design wind speed, and that was covered in the previous PowerPoint presentation. We then determine the design wind pressures for the windward, leeward, and sidewalls based on the dimensions and configuration of the building. Once we've got that, once we've got the wind pressures, it's quite simple to go ahead and determine the forces on structures, because we know that force equals pressure times area, okay? Now, this is the equation that we need to use, okay? This converts our wind speed to a pressure, okay? Now, this 0.5 times the density of air, that's pretty simple because it's given to you. We use 1.2 kilograms per meter cube, okay? For the design speed, that's what we calculated in the previous slide. C-fig is what we call our aerodynamic shape factor. Okay, now this takes, well, as its name implies, it takes into account the shape of the building. And we've got a dynamic response factor. We're just going to use 1 for that. So the only thing we need to look at in this slide is how to determine this C-fig here. okay? Because we're given the density of air, we're given the dynamic response factor, and we've covered in previous slides how to find the design wind speed. Okay, so the subsequent slides will concentrate on this aerodynamic shape factor C fig. To calculate the design wind pressure, we calculate the pressure coefficients for different parts of the surface of the structures, C fig. We typically find coefficients for the external pressure, okay, and E, and the other for internal pressure, I. In these notes, our example will ignore the internal pressures, and we will focus on the pressure on the windward and leeward walls, okay? We're going to keep it simple. Just the outside pressures pushing on the windward wall and the pressures pulling away from the leeward wall. Okay, so here's another equation now. How do we find C fig external? Okay, this is the external aerodynamic shape factor. Okay, so we're going down another level of equation. We need to find the external pressure coefficient, the area reduction factor, combination factor of external pressures, local pressure factor, and porous cladding factor. And you're probably going to be happy to know we're not going to worry about these K factors. We're going to assume they're all one, okay? This is not an advanced structural design course. We don't have to go into all these factors. I just give you an idea, okay? So we're going to concentrate on finding this external pressure coefficient. Okay, so how do we find the external pressure coefficient? Firstly, we need some definitions. Okay, in the code for various buildings, you've got, it gives you definitions of windward wall, leeward wall, side walls, the up roof and the downside of the roof, I suppose. So they call it windward wall, okay, W, side wall, leeward wall, okay, that should be quite straightforward. Upwind slope, that's what they call upwind roof slope. This is the downwind roof slope on the other side. And you've got the average roof height, okay? So the average roof height is obviously halfway between the ridge, you know, the apex and the, I suppose the bottom of the ridge here. Okay, so those are some definitions for these 7 factors that we need to consider to determine our external pressure coefficient. Okay, for the windward wall, okay, you've got, if the height is greater than 25 meters, use 0.8, okay. For buildings on the ground, when the wind speed varies with height, it's 0.8. When the wind speed is taken for Z equals H, okay. For elevated buildings, we use 0.8. Elevated means it's up on stilts or something, right? So this is what we look at here. So if it's greater than 25 meters, we just use 0.8 to convert our winds to put for our CPE, right? And that also is actually happens to be our aerodynamic shape factor as well value. And for buildings on the ground, 0.8 when the wind speed varies with height, or when wind speed is taken for Z equals H. Now, why do you use 0.7 when the wind speed is taken for Z equals H? Well, that's because Z equals H is the maximum height, right? So you're already being conservative by using Z equals H. So we can use a lower value of 0.7 for our wind pressure. But when you vary the wind speed up the building, okay, you're taking a more accurate point of view, but you're not taking a conservative assumption. So we use 0.8, okay? We will be using 0.7 for our purposes, okay? Because we're going to use Z equals H we're going to use the wind speed at the basically the highest point of the building. Okay, so that's for your windward wall. Very simple.
You say,
Now, yep.
Sorry, did you say that so elevated building, is it like on a platform or?
Yeah, if it's on a platform, okay, so it's lifted up on a platform or something, right?
Okay.
Yeah. Okay, leeward wall. Now this is more complicated. It depends. Well, hip roofs. You know what hip or gable roofs are? I can show you in a minute. Okay, online. Okay, it depends. You've got to take into account your roof pitch. Okay, and your D over B. Now you know what D over B is because we've looked over here. Okay. actually so you got D here and you got a B here, right? So D is, so you got to look at this carefully, okay? B typically is the width of the wall facing the windward, facing the wind, right? So, and D is the side wall dimension, okay? So we've got to calculate out D over B, and then we get pressure coefficients of for external for the leeward wall. Notice these are negative values because the leeward wall, obviously, the wind is pulling, the wind pressure is going away from the wall surface. Now for roofs, you've got various, it's quite complicated. We're not going to need to use this for our purposes, right? We're going to just look at a box, like something like a shoe box, to calculate a lateral load on the wall. Okay, so, but that's just there for your information. Okay, it gets quite involved. So here's an example. A lateral force from wind on a flat roof structure. Now imagine you're given this, you've calculated a design load like you did in the previous slide. Okay, so you've gone through a process and you've got a wind speed, a design wind speed of 37.8 meters per second. We can then calculate the forces on each of the floor diaphragms and roof from the wind. Okay, so the first thing to do is you need to work out, we need to go back to your formula, and you need to work out CPE and CP for the windward wall and for the leeward wall. Okay, so let's have a look at CPE. We got this table here. For the windward wall, I said it's very simple. We're just going to assume 0.7 because we assume that wind speed is for the height of Z equals H. Okay, and we're assuming these K factors are 1. So the windward wall factor is 0.7. Now for the leeward wall, let's look at D over B. You've got D, which is the length of the side wall divided by the length of the wall facing the wind. Okay, so we've got 0.5. Okay, from table 5.2, use, I'm not sure what that means, use CPE equals negative 0.5. So D over B is less than 1. So we're over here. And we've got a flat roof, right? So our pitch, this has made it easy for you. So our flat roof is less than 10. So we're just going to use negative 0.5 for our factor, okay, C fig E. So this equals negative 0.5. Okay, so I just want you to write down now, C fig E is 0.7 for the windward, and C fig aerodynamic shape factor for the windward is 0.7, and for the leeward is negative 0.5. So just make a note of that. Write that down first. Okay, and make a note of V design equals 37.8 meters per second. So just make a note of, write that down. Now, once you've done that, I want you to do the wind pressure calculation twice. One for the leeward wall and one for the windward wall. Remember, you got 0.7 for the leeward wall, and you got negative 0.7 for the windward wall, and negative 0.5 for the leeward wall. Okay, so you can use this formula now to get the design wind pressure, windward wall and leeward wall. Okay, so do that calculation. Okay, you've got the windward wall. Okay, you've got 600 PA for the windward wall and negative 429 PA for the leeward wall. Does that, do you guys get those values?
Yep. Yep.
Okay, now let's work out the force. I should have told you to work out the force as well. Well, the force on the wall is just, you've got the area of the wall. Okay, so you've written down the pressures. So I want you to calculate the force. You probably saw the answer, it doesn't matter. Just go through it, calculate, you know, the area of the windward wall and the leeward wall, they're actually the same. I want you to calculate the forces now on the wall. the total force on the wall. Okay, guys, so for the windward wall, you have a force acting toward the wall of 173 kN, and on the leeward wall, a force of 124 kilonewtons. So this is what you've got. You've got a total force then on the building of 297 kilonewtons. Now, now let's look at the trip. That's the total force, right? But often, you might have a wall with studs here. How does the wind apply the? How does this wind place pressure on the walls? Well, the way pressure is placed on the walls is like this. I'll just draw a figure for you. Okay, so if you have wind coming into a wall, how does this actually translate set between each of the stories? What happens? This is the way the thing works. Okay, it's considered to act like this. Okay, what it is these walls are considered to be like simply supported slabs. Okay, we've done gravity loading before, but this is horizontal. These are like slabs that are simply supported between the roof and the floor diaphragm. So you imagine the wall trying to, deflect inwards like that. Does that make sense? So what happens to so now let's look at one of these studs. Say if you've got a stud here, right? It will look, this stud will be deflect like this as well. Okay, that's the way it will deflect. And what's the loading on the stud? Well, it's this red tributary area. So for this particular stud, it's this red shaded area here on the second floor for this for the second floor wall. Does that make sense? So it's the tributary area is 1/2, just like, imagine these are beams, right? But you're looking at them vertically. Okay, so the tributary area is 1/2, halfway the distance between each stud. Okay, so for this one here, you've got, for this stud, you've got from the second floor, that's a tributary area. For the entire stud, it's from here, it's that entire tributary area here. This stud on the first floor will look like this. Okay, it will deflect like this, and this is the area loaded by the pressure. So it'd be easy if you could just flip this. It'd be very easy to understand, perhaps easier. So I could just paste that there, and if I rotate that, I think it'll work. Okay, so imagine if this was a floor area, right? And you got pressure on it. Basically, the imagine this is a floor, and they're being deflected, simply supported between the the ground, the first floor diaphragm, and the roof diaphragm, and you can see those studs deflecting, right? Okay, you can see the wall deflecting, and what comprises the wall? It's the studs, and the tributary area of the studs is the shaded red area. Does that make sense, guys? So you can treat, what is the UDL on the studs? It's just the width of the tributary area times the pressure, isn't it? Okay, so it's important for you to know how this mechanism works. And what happens, okay, so this windward pressure gets applied to the walls, and the walls apply them to the diaphragms. Okay, so you can see here, this first floor diaphragm, or the first diaphragm, will take twice as much force as the ground and the roof, because you can see, if you look at it from the point of view of the diaphragm, this, for the first floor, this red area is the tributary area for the diaphragm, right? It's got twice the tributary area of the roof and twice the tributary area of the floor. Okay, so for this 3-story structure, how much of the windward force goes into the ground? Well, I've told you it's 1/4. How much goes into the first floor? It will be 1/2, and 1/4 will go into the roof. Okay, So you can do the same, you can do it for the windward wall and for the leeward wall. Okay, so does that make sense now? How this works? Any questions on that?
No, that makes sense. Yeah.
Yeah. Okay.
Thank you.
Good. That's how. So just remember, that's how it works. Okay. Just think of it as a floor. You just turn it up to rotate it 90 degrees. It's just like a floor, isn't it? And these are like floor slabs supported by these. Imagine these diaphragms, the floor and the roof, to be long beams, right, over which slabs are supported. Okay. So that's about it. So is it okay? I think there's quite a lot to take in today, right? So no one will complain if we finish half an hour early, will they?
You know, that's good. Yeah.
It's okay. Yeah.
Okay. So look, I'll try to have your, when's the assignment due? Have you submitted it yet, or?
Yeah, that was due today, no?
Oh, okay. So if you submitted it, I'll get that marked pretty quickly and I'll get a new assignment out for you as well. Okay. So,
Okay.
So the exercise we've done today, just go through them a couple of times. Okay. Get used to finding the documents, and in the test, we'll probably give you a question on wind. Okay. It shouldn't be too difficult for you, but it is a lot of new information to take in. Okay. So I'll see you guys next week then.
Thank you.
Thank you.
Okay. Have a good one, guys.